Okay, welcome to today's lecture. So today we're going to focus on two topics: mixed language programming and creating a software build environment for your Fortran code or any other code for that matter, how you should build your code in an efficient manner. But we will start off with mixed language programming. And as you probably have experienced yourself, it's not always possible to use only a single language in many projects. So in many projects, you have the need to be able to integrate, for example, Fortran modules and code with Python, for example, or it could be you have C++ or C code that you need to interface with Python code. And I will go through some of the topics of that today. So let's see here. I'm just going to download examples here in my notebook that will be used. The examples are in a folder called F2Py. You will also get this tarball after this lecture. So, how do you integrate two languages? So, Fortran and Python are fundamentally very different languages. So, Fortran is a compiled language that generates machine code. And Python interprets every source code line by line, and interprets that to machine code line by line. And that it also has a very different handling of variables. But Python has from the beginning always had a way of integrating other languages into itself. So you can create modules, special kind of modules that are called extension modules that are implemented in the C language. And these modules use to implement them, they use the Python API, which is a C-based API, for creating these modules. And they behave as any other Python modules. You can't see any difference, and you probably already used some of these extension modules already in this course. So, for example, NumPy is a C-based extension module. So it's a compiled module that you use like any other Python module. And many of the core libraries in Python are compiled from C code. However, it's not that easy to implement a Python extension modules in the C API. So the following screen here shows how that implementation looks like. So this is a C code. And the first thing you will notice here that we have the Python include here, python.h. So when you install a Python, there is always, it comes with a header file for C, which provides the calls that you can use to implement this module itself. So in this case, we will implement a module containing a sum function for summing two values together. So in this case here, we create a function here with a specific syntax. So you can see here there are Py object, that is a generic reference to a variable in Python. And you see also that there is a Py object in the call, two of them, so two variables. And inside this routine here, we implement the actual function. So in this case here, we will add two numbers together. That comes in from the argument of the function. Then we have to do some stuff to parse this input that comes from Python. And then we need to do so in this case here, A and B will be assigned the incoming variables here. So we go through the arguments here, which contains in the args, and then we assign the variables in our code, calculates our output value, create the return value here, which we return out. And then we also have to create a module definition here in C. We call the module sum, create a help function, initialize the module. And if you want to interface with, for example, Fortran, it gets even more complicated because there is no Python API for Fortran. So you need to interface the Fortran code with C code. So this is too complicated to be able to be efficiently used. So there must be some easier way to do this, and there is. So when you have installed, for example, Anaconda or any Python or NumPy packages, there is a special tool called F2Py. And what that tool does, it translates the Fortran code and creates Python extension code. So basically, F2Py looks at the Fortran code and creates the corresponding C code that is required to create an extension module. So you don't have to think about the C API at all. You can just think about creating your perfect Fortran module that you want to interface with Python. The nice thing with F2Py is also that it handles NumPy arrays as Fortran arrays. So the NumPy arrays are passed as the normal Fortran arrays over to the Fortran code, and you can access them very efficiently from within Fortran. It's a command line tool, so you have to open a terminal or a command line prompt and type the commands to do the compilation and creating the module. However, there are some warning here. Because it's a kind of compiler, it creates C code, and when you compile C code, you get error messages that are not related to your own code. So it can be somewhat hard to debug the errors in the output. But I usually do. I try it out and see if it works as it should, and then I try to update it and look at the code to see what I did wrong. So we start with a simple example here. So you do this basically the same as the example in the Python C API. So in this case here, I have a single subroutine here, simple, that takes two variables as input, A and B, and one output variable, C here. So intent in here, this is the way to tell the Fortran compiler that these variables are coming in. They shouldn't be modifying the subroutine. Intent out is the output variable that is assigned in the subroutine. And the Fortran compiler will check so that you don't do anything that breaks those rules. The interesting thing is also that if you use this and use F2Py, F2Py will use these attributes here as hints for generating code. So if it says intent in, F2Py knows that these are input variables, and it will generate special Python code for that. If you have intent out, it will generate special code for an output variable, C in this case. So it will read the code and generate the C API. So how do we use this? So on a command line, you enter the F2Py command. Then you specify what your module name is going to be called. So, and you have a specifier using the -m switch. And then you give it a name, in this case, simple. Then we have to compile the Fortran code, and that is done with this -c. And then we give the source code files for the Fortran code here. So let's see what happens when we run this here. It produces a lot of output here. So you can see here it creates C code, compiles with the Fortran compiler. And if everything is okay, it should end with removing build directory. Then you know it has created the extension module correctly. So you can see also here that I have simple F90 here, but I also have a simple.f.so. And that is the compiled Fortran module in a way that you can load it from Python. So if you're doing this on a Windows machine, the extension will be PyD. So Python dynamic module, so PyD. But on Linux and I think also Mac, it will be simple.so something. So what can we do with this now? So to use this module, we need to import it just like any other Python module. So in this case, import simple. One other nice feature with F2Py is that it actually creates documentation for your Fortran module automatically. So reading your Fortran code, it will annotate the interface, and you can print the documentation for that. And you do this by specifying simple.doc. And if you run this, okay. Okay, I switched to a backup computer. So I have this here. So I have the simple code here as well. So simple.f90. So I do F2Py -m simple, and then I do -c simple.f90. and that compiled, and then I do I create variables a equals to 42, b equals to 2, c equals to simple. So now it is a simple model, and I have my, I think, call it the function is also called simple. So it's simple a comma b. I have to import simple first. So like that. Now you can see here, C is actually 84 now. So it went into the Fortran code and back into Python again, and creating a Python object, C. I don't know why it doesn't work here, but yeah, I have to figure out. It worked in the last course. Okay. The documentation as well, I will print that out as well. So we do the print simple doc here. Now you can see here that it prints out here. This module simple is auto-generated after pi, and then it contains the function simple with the parameters a and b, and it returns C. I can also print detailed instruction documentation on the simple function. So I can do print simple.simple. Like this. And now you can see here that this is a wrapper for the simple function. It has the following parameters: a input float, b input float, and it returns a floating point value C. So that's nice. So how we will now do a bit more complicated example where we create a subroutine for multiplying matrices. So we will use the Fortran routine matmul to do this. And then we'll create a subroutine here called matrix multiply. It takes A as an input here, and then we also provide the sizes of the arrays as input to this routine. This is not a big problem when you generate here the code. Python will, or the F2Py tool will automatically figure out which of the parameters are used for declaring the sizes. So you actually don't have to call the matrix multiply routine with these parameters. They will be optional. So what we'll do now is we will create a array module called array1, and we will compile this subroutine here using the C command here. I will do this now in the command line prompt here. So I do F2Py minus mr1 minus C F90. See perhaps. So now we have a array1 here extension module here, and on a Linux-based machine, it's a bit more extensions or suffixes added to this routine here, but the ending extension is SO, and that's for share obviously. So this is actually a binary file. So we do IPython here again. We do import. Let's see here. We do R1. The first thing I usually do when I do extension model is I print the documentation. So print R1 dot, just to make sure that I actually get what I want in the binary module. So you can see here it contains a function here called matrix multiply a comma b, and you can see here it has the shape a comma 0 and shape a comma 1 here, which are the sizes of the arrays. And we can also print, I'm sorry, matrix multiply. Now you can see here the documentation for the matrix multiply routine. And as you can see here, the matrix routine is called matrix multiply. It has two parameters, A and B. And you can see here there are brackets here around R, S, T, and that is because those are optional. They will be provided automatically by the wrapper function that we created now. And you can also see here that C was an intent out variable, and it ends up on the left side of the generated wrapper function. And you see here that is a rank 2 array with floating points here with the bounds R, S. Now you have an input rank 2 array F with bounds S, T. So let's see here, we can use it. I will import. I'll copy the code here for this. I have a array, a B array, and a C array here. So now what I can do is one other thing that is important to think about here is that we created a C here, and we can see here that this line here will assign a C with an array, and that will be overwritten. So the C array we created here will not be preserved; it will be overwritten. So we just check first here the ID of C. You can see here it's n by 9264, and then I do C equals to R1.matrix multiply A, B, and then we do print ID. Now you see it's not the same. It's 7520. So when we do this, the wrapper will create a new array and return that. And you can see C here is the matrix multiply. So it seemed to be okay. So this could be a bit inefficient in certain cases, except if you have large array structures and you use the normal standard intent out, the wrapper will generate and create a new array and return that from the routine. For many cases, it could be okay, but for other cases, you need to kind of handle this in a bit of different way. So let's look at the other example here. Now we change, instead of having the output array as an out argument, we say intent in out. And in Fortran language, that means that C can be used both as an input array and also as an output array. So let's see what happens if we compile this. So now we have array 2 here, so we do f2 pi minus m r2 minus now we do IPython. First we import print it out, see what we have in this r2.doc. Okay, we have a multiply 2 routine here. And now you can see that all the arguments are on the right side in the parentheses. So C is not on the left side, so it's not a function anymore, it's a pure subroutine. That is because we use the in-out attribute when declaring this. Let's see if we matrix multiply 2.doc. And here you can see also input argument to have rank 2 array A, rank 2 array B, and then an input output rank 2 array F with bounds R, T. Now we need to create this array before. So now we have to copy these 3 arrays again here. Now we do print IDC. Here is 1440 as end of it, and then we do add to matrix multi 2 A, B, C. So now we provide C as an input to the function and not as an assignment error on the left side of the function call. And now we do print ID C. Now I see it's the same array again. So it was passed into the Fortran code, modified inside Fortran code. And if we print C now, it should be a matrix multiplication here. So that seems to be okay. So now we create the 2 arrays, we pass them over to Fortran, and then we got so Fortran wrote the results into the C array. Another thing that we haven't discussed here is the last argument in when we create our arrays. The order equals to F, and it's not strictly required to have order equals to F, but if you pass, so what that means is that NumPy will create arrays in the Fortran storage format that is, I think, column-wise. If you don't do that, it will create arrays in C storage format in row-wise. And if you send over a normal array to a Fortran, the wrapper will create a new array in the right that works with Fortran, and that is very costly. If you create arrays directly in the order equals F, the array will be passed by reference. There are no copies made. It's it's most efficient way of passing an array over to Fortran. FTPy is a bit dangerous because it will generate wrapper code that handles every situation. But just remember, if you want to pass over things efficiently, use order equals to F. So now we will also look at how you can use, you can export modules as well. So if you want to have an entire module exported to extension modules, that is no problem. It's just that you compile the module, and FTPy will automatically generate submodules for the different modules for you automatically. So in this case, we have a module containing our previous routines here. So we have the sub matrix multiply. We also have the matrix multiply 2. And what we do is then we compile both of them into a matrix module, and we use the source code matrix.f90. So let's see here. F2py minus m matrix c matrix.f90. Now you can see I have a matrix shared object here. So I do IPython. Right, we do just import matrix here. We do our print. So now you can see here I have a module matrix in my module. So there are 2 module concepts. The FTPy will generate a binary module. If you have multiple modules that you compile, it will create submodules in your extension module. So in this case here, this matrix module here contains a matrix submodule, and that submodule includes matrix multiply and matrix multiply 2. So if I want to access those functions, I need to do print matrix dot matrix multiply, and just print the doc here. So this is how sorry, matrix.matrix. You have to do it twice here to kind of get this here. So what you usually do if you have multiple modules as an extensions module is that you do it a bit differently when you import them. So we do matrix import star. Now we have a matrix module directly here. So now we can do print matrix.matrix multiply. Which is more what we want. Another option is that you have a meta module that calls something my finite element system, and then you have multiple modules underneath that one. Yeah, so this was also if you want to delete a module, you can do that using the delete command actually. So if you have loaded a module, it's possible in Python to delete it by calling del and on the module name. So everything in Python, even the modules import, are dynamically constructed. So you can always remove it. So that was a little bit about how you interface Fortran with Python. I think one important lesson for this is that you can, if you have want to create a more flexible application or computational code, one way is to take your existing Fortran code, modularize it, provide an interface in Fortran which you want to provide to Python, and then you compile wrapper modules for your code. And then you can create, instead of using input files, you can define your input directly in a Python source code, run it directly and control your simulation from Python, which actually makes your existing static Fortran code dynamic instead. So you can experiment and interact with your Fortran code in a way that you couldn't do before with your normal Fortran code. So there is also some other tools. If you're from C, there are Swig, for example, for generating interface code for multiple different languages. There are also Boost modules for generating extension codes from C++ object-oriented code as well. So Python can be seen as the glue language that can glue different parts together to create a single system. And I think that F2Py is exceptionally well done for Fortran. It's almost, you don't have to think too much, you just compile it. Think about some of the things warnings here regarding the ordering of arrays and also the intent in-out, for example, is also important to think about. So I think we will do a 10-minute break, and then we continue afterwards with your software environment, build environment for Fortran as well. So we'll take a short break now. Okay, so in the next part here, I will go through some tools that can be very useful when you do Fortran development. So up until now, you have probably either compiled using the precompiled templates in Qt Creator or used the command line Fortran compiler to compile your source codes manually. So when your code becomes larger and grows, you will probably need to do more maintenance on your project. Somebody perhaps wants your code to be able to run on multiple different platforms, to be able to run in an HPC computer in Europe, or an HPC computer at Lund University, or on a Mac, or a different way. So you will get requirements for being able to build your code on different platforms. You can, of course, automate some of these things using scripts, but for larger projects, scripts are not suitable to handle source dependencies, and often will also require that you rebuild everything every time you run your script. Because if you have large program, you can have thousands of source code files that needs to be compiled. And if you modify one single source code file, you probably don't want to recompile everything in every iteration. So you need to kind of figure out to find some tools that can help you automate this. There are two major tools that you can use. One is Make, and there is a higher level tool called Cmake as well that uses Make underneath that can help you solve these problems for you. So we start with the basic tool which is called Make. So Make is a very special software that builds software from very specific rules. You can also in this syntax that you specify in your Makefile, you can handle dependency of different files or steps in your build. So it can figure out, for example, if you build a certain module that if that changes, it has to recompile different modules. It can also detect if a file has been modified, then the depending files, the object files need to be rebuilt. Make is available on any platform, so you can get the GNU Make tools on Windows, Mac, Linux, anything you can find where you can build software. It's a bit non-intuitive in the beginning, but I think it will be, after a while, you will see the logic in it very clearly. So the basic syntax of a Makefile is, let's see if I can annotate here, is that you specify a target, basically what you want to build. And then an optional line here is the dependencies, is what this goal or target requires before it can build. And then you have to specify a temp character here, and then you specify the commands to achieve this target. So a very simple example here could be, I want to zip a file, for example, and I have the target is then my goal or target is myfile.gz. So that is the compressed file. And it depends on a source code file or a text file, in this case, myfile.txt. So here I have a relationship here. So to build my zipped file, I need the text file, of course. So it has a dependency on the text file. And then how do I get from my file to myfile.gz? This is a Unix-based example here that you cat my file that displays the file output to stand output. I pipe it through gzip and output it to myfile.gz. So this part here is the recipe for achieving my target. And the target depends on my file text, and to get from myfile.txt to text, I have this recipe here. So I will do this live now. Hopefully it will work. So I will go to my other window here. So here I have two files here. I have my Makefile. So the Makefile, the default file name of a Makefile is Makefile with an uppercase M. And if I look at this file, it looks like this. I have myfile.gz, myfile text, just like in the PowerPoint. There is also a target here, clean, that is has no dependencies. You can call it, and it will remove the GC file. And then I have a myfile.txt here, which contains a little text here. So if I want to create this zip file, I can just type make. And you can see here that it takes the default target and creates the zip file. So if I list my files here again, you can see here that there is a zip file called myfile.gz. So it apparently worked. Now, if you run make again, you will see that it says Makefile, myfile.gz is up to date. So make will detect there is newer version of the text file that has been created. So I don't have to run the recipe again because the file is already up to date. So, but what if I go in and edit my file here? So my file. So I save my file again, and now I do make again. Now you see here the text. Okay, the text file was changed. So now the GC file is not updated anymore. So now I have to rebuild the zip file again using the recipe. But if make again, it will say that it's up to date. I can specify a specific target to run by specifying make and the name of the target. So in this case, I will try clean. Now you see it will remove all the gzip file here. So now there is no zipped file. If I run it again, go crazy. I can also do make my file as well. So you can specify the target as a first parameter of the make tool. So how do you use this to build code? So to build an executable file, you need to compile source codes into object files. You have to link the object files into an executable. Well, object files depend on source code files. Executable depends on object files. So you can see here that it's a clear case to use make to do this. So in this case here, we want to, our ultimate goal is to build myprog, which is an executable code that's executable I want to achieve. Myprog depends on the myprog.object file. And to achieve the myprog here, I link together myprog.o and to create myprog here. And you can also see here that I have a second dependency here, the target. So myprog.o, how do I achieve this file? Yeah, it depends on my Fortran source code file. And then the recipe to create myprog.o is myfortran compile myprog.f90. That would generate the O file. And then this dependency can be built as well. So now you see here I have a Makefile with two rules: one to create executable, one to create the object file, and they all have dependencies. So if I run now here, it will do two steps. So it will compile. The first thing it notices that the myprog executable has a dependency of myprog.o. Okay, then it goes to the next rule: how do I achieve myprog.o? I have to compile myprog.f90. So it says that, okay, it depends on F90. So if it changes, you have to compile that. So the first step it does is it compiles the myprog.f90. That will generate the .o file. And then it can compile the executable into this to the executable using gfortran myprog.o, output myprog. So of course you learned also that you can compile your program in a single step in Fortran. Why do we do it this complicated? It's because, of course, you can use a single command line to build everything, but Fortran will build every single file when you do that. By dividing up your code into multiple targets, it will only rebuild the required files. So of course here, if I remove my executable file, myprog, and I do make again, it will only run one single thing. It detects that myprog.o already exists and is up to date. The only thing I have to do to create an executable is to link. Same thing if you have multiple source code files with multiple rules, it will notice which of these files has been modified and only recompile those files. So in the second example here, now we have a bit more complicated program. It has a module now, so my module.f90, and I have so then I have to create two object files. So my program now depends on my module.o and myprog.o, and I need to compile them in separate rules. So here I have 3 files. I have a Makefile with my rules. And if I run this now, you will see here that it will first build my prog, and it will be my module.f90. And then when all the prerequisites for my prog here, which is both of these, it will compile and link the program together. The nice thing with this concept is now, for example, if I modify my module here, so I do touch my module.f90. Now the my module.objects file will be not updated anymore because there is a newer source code file. If I run make now, it only rebuilds my module. It doesn't rebuild the myprog.o because that is already up to date, so you don't have to do that. And then it links together, of course, because that step is always required. And if I do it again here, you see myprog is up to date. I don't have to do anything. Yes, that was that. There is, however, something that is specific to Fortran, and it's the module dependencies. So when you compile a Fortran module, there is a special file created called the module name and the .mod. And that mod file is used by other modules that are using modules. So if a module uses another module, when you compile that module, that mod file must exist before you compile the module using that module. So you need to kind of make sure that the highest level module is built first, so that the mod file exists for the lower level modules to be able to build. And of course, Make can solve this again for us, so that's no problem. So now we have a slightly more complex build. We have a module main and a module truss that needs to be built. And if you, so let's see if we can try this here. So when you try to build this, it will complain now because use truss. So module main uses the truss module, and it can't find the truss module to reading it. So the problem here is that we need to make sure that the module truss is built before module main. And we can do that. We can add a dependency here. So we can say that the module truss.o has a dependency on module truss f90. No, sorry, module main here. The module main, which uses the truss, we add the object file here to the dependency list. That will make sure that module main will not be built before module truss here, because this has a dependency on the object file of the module truss.o. So let's see, we have it here. We have module main here, module truss, G4tran module main, module truss, myprog, and you see here that we have added the object file here, module truss.o, as a dependency. So you have to be able to build module main. This one also needs to be built. If we do make here, you can see it builds first module truss now, and now module main is built after module truss. And if you look in our source code tree here, you can see also that this truss module here is built when you build the module. And this mod file contains information on type information on the module that must exist if you want to use the truss module. So that is nice to be able to do that. So if you want to make the Makefiles a bit more efficient, or you don't have to rewrite a lot of things, you can use variables in Make. That would also make it more easy to configure and to port your Makefiles in different configurations. They work a lot like when you have script variables in Bash, for example. It's easy, you just assign a variable name to a value, and you can use it using the $sign and the variable name here in parentheses. For example, things that can be changed depending on the configuration is, for example, convention is to use FC for the Fortran compiler. So I have FC equals to Fortran, gfortran, and my Fortran flags here are C for compiled. Here you can add optimization flags as well. I have an executable here for my name of the output executable. So now I replace my executable name here, my rule here, to executable, and instead of the Fortran compiler explicitly mentioned here, I just do -fc, and then I do myprog.o, and do that rule. I add my compiler flags here when compiling my code, and also here in my clean rule, I reuse the executable again here because that needs to be removed. We can, however, create even more generic Makefile. So a lot of the things that we have to rewrite a lot of rules and which make it non-generic or very specific to every project. So there are some macros that you can use. For example, $A is the target of the current rule executed. $up is the name of all prerequisites. Name of the first prerequisites. So how does this look? So for example, executable myprog, I list object files here. So this first here, that refers to the prerequisites. These are the prerequisites here, the dependencies basically going in here. Output here is the name of the current target being executed. This code is myprog here. So I don't just specify myprog here. I just do $at instead. So then as you see here, the rule becomes very simple and generic to the most applications. You can also do, in this case here, this here refers to myprog.o. This one here should refer to the first of these prerequisites here as well. There are some other rules that you can use that make it more easy to maintain, so-called suffix rules. So instead of specifying explicitly every file that you want to, a rule for every file that you want to compile in Make, you can specify rules how to convert, for example, a .o suffix to a, so .f90 to a .o suffix, and you create a general rule for compiling any file with those extensions to get to another extension. So you can say a recipe for converting a source suffix to an object suffix. How can that look like? So in this case here, you can specify, for example, .f90.o. So that is a rule that says that defines how you create an object files from a .f90 file. So in this case here, I just specify here this basic rule. So this is the target here, and that will automatically compile every F90 file or create a rule to get the .o file automatically for you. The suffixes must be supported by Make. I think most of them are already there, but you can tell Make which suffixes you will use. For example, .f90, use the suffixes command here to specify that F90 is correct suffix, F03 is another one, .f or uppercase .f. Now some more, you can also use wildcards here to create lists of files, which can be useful if you have a large project and want to compile everything in a directory. You can use the wildcards to substitute multiple files in that directory. There's also a special function here to change the names of the lists to, for example, removing suffixes or adding suffixes, which can enable you to create even more generic files. For example, here, I can create a list of all my F90 files in my directory. So I can do F90 files colon equals, so you use a special notation here, colon equals to $wildcard.f90. That will create a list of all your source code files. Then we can create a list of all the object files in my project by using pos substitute and substituting all the .f90 suffixes in the list with .o from the F90 files list. Then I get a list of all my objects, potential objects in my code. And then I can create a rule that is extremely generic. So to build my executable, that will depend on all the objects in the code or in my directory. And I will compile using the compiler here, and then it takes all the objects here is this dollar arrow up here, and then this is the name of the target here. So in this case, executable. Now we have a rule that is completely generic for most projects. You don't have to. There is no explicit mention of anything project specific here. So you can define all your special configuration options in the beginning of the file, and then you can just use these rules to make sure that you build everything and reuse them in other projects as well. Then there are also pattern rules, very similar to suffix rules. You don't have to use the suffixes for additional supported suffixes. And this is also the recommended way of doing it in Cmake. It uses the % operator, just like the wildcard functions. So in this case, instead of the .f90.o, you do %.o colon %.f90. That means that an O file in the directory will depend on an F90 file, and this is how you compile it. I still need to specify a relationship between the modules in this case. So because my module depends on my utils here, so make sure that my utils is built before my module.o. But this you don't have to specify in a recipe, you just specify a single line that defines the dependency. So here I list my F90 files, I list my object files. So you can see here, this is the dependency here. So objects here will be a list of object files for the project. And then this rule is automatically applied for creating an object file of the files in the directory. So let's see if we can find this one here. So now you can see I have a Makefile, and this looks something like this. I have my configurable options up here. I have a single rule here. I have the dependency for my module. I have a dependency here on the general rule here to get from .o.mod here, F90, and a clean rule. So let's see what happens if we build here. So the result is the same as we had before, but now you don't have to specify specifically rules for every source code file. You have a single rule that handles all of the source code files. And you can also see that if you touch a single file here, my utils, it will only build util. Of course, because my module depends on utils, it will also build the my module here. And clean will remove everything here, and we're back to the beginning again. So that was make. Now we will try to make it even easier. So we go to Cmake. So Cmake is a cross-platform build system, and Cmake actually doesn't do the building and heavy lifting itself. What Cmake does is it can create build files for you. So from a very intuitive language, you can specify how to build your projects in a perhaps more comprehensible way than Make. But the result of running Cmake is actually Makefiles. So it will generate Makefiles or project files for example, Eclipse, Visual Studio, and Xcode. So if you have multiple developers on a project, they can use whatever build system they want to develop your code. So if you're a Windows developer, you can generate project files and open your project in Visual Studio and work on it. And all the rules that you find in your Cmake file will apply in that way as well. And if you're a Linux user, you can do it with the command line, for example, to generate Makefiles and build the code using Makefiles. It's also a language, so you can create a logical flow in your build system, so it can actually take decision depending on your platform. So you can check for different things, and it can also have branching. So depending on the platform, you build in different ways. So how do a Cmake file look like? So always when you start a Cmake file, you specify this Cmake minimum required. So this is the way of telling the Cmake compiler which version of compiler it was created with. So check the version number, and then you specify the version of the Cmake tool that you used, because that first line also tells which kind of syntax that is used for, because Cmake has been updated over several versions. By specifying this, you make sure that it uses the correct syntax for the Cmake file when you create it. But yeah, it's just boilerplate. Then you specify the name of your project. And that is not the name of the executable. That is name of, so I mean, a Cmake file can contain multiple different targets. So you can have an executable, you can have libraries, different built in the single, using a single Cmake file. Then we have to make sure that we enable the language Fortran, because that is not by default activated. So enable language Fortran, so that will add functions and logic for building Fortran code. Then you specify, I want to build an executable, so now add executable. This is the name of the executable, and this is a source code file that is used to build the executable. That is everything you need to kind of create the build system for a Fortran code. So let's see if we can. I will do it on the fly here. So let's see here, make clear. And the Cmake file is called Cmake list.txt. So it's a bit odd, but this is the default name of the Cmake list file. So I do vi. I think I can do 3.8 or something. Yes. And then I do project, simple. I do enable language Fortran. You see here that the editor actually recognizes the Cmake list files automatically. Then we do add executable. Then I do vim simple.f90. That's correct. So what I can do now, so now you can see there is no Makefile, so I can't write anything here. So I need to create a Makefile. The way you do that is that you run Cmake. So you do Cmake. In this case, I do it in this directory here. Haven't done. Okay, I have to go to Cmake. Cmake dot. Okay, let's see if I can just fix that one. Okay, so now. So when I run this, you say configure it done, generating done, build file has been written to my directory. So now you can see here, I have a Makefile. And we can look at this file as well. It's pretty large, but you can see here that it generates a lot of the things that we looked at before in the Make, but it's much more sophisticated than our simple Makefiles that we did before. To build it, I just type make, and you can see here it handles all these things automatically for us. And we have our executable file here which we can run. Yes. One thing that you can notice also is that if we look at the directory now here, it's full of additional files that we probably don't want to maintain. So I will make clean. Then I will remove all the other files that was created here. Cache, make, install, make files, and also Cmake files directory. So now we're back to normal again. What you want to do when you use Cmake to not fill your source code directory with special extra build files is that you create a simple build in your source code. You create make clear build. You go into that build directory, and in this directory I do Cmake, and instead of using Cmake dot, I do Cmake dot to specify the upper directory here. Then it will look for the Cmake list files in your source code, but all the build files will be created in the build directory. So now you can see here it checked here. That is also something that the Cmake will do, is will check the compilers, which compiler is used. So you can see here I will use the 10.3 G Fortran Compiler. It will check that it works. And it's also checking here for Fortran Compiler. Does some generic checks here. Now you can see I have all my build files in this directory. When I build it here, I get my executable here as well. But my source code tree now is clean. So I can very easily also remove the entire build directory in one go like this, and then I can rebuild again. So there will be a lot of files created when you build using this method. You can also compile for releasing or for debugging. So when you compile for debugging, you create a non-optimized version of your code for being able to step through the code in different ways. But when you release it and want to run it more efficiently, you can build a release version of the code, which is with all the optimization flags defined automatically. And we can do this with our simple code here. We do Cmake dot minus d Cmake build type equals to release. I think I have to do it. Now I will do, just to show you that it will use compiler options that are missing. I will do make verbose equals to 1. You can see here now that the compiler now uses the O3 flags here. It also defines that this is not a debug build, so it will compile automatically with the default optimization flags on. And if you do Cmake debug, and you do make here, you will see here now that it will add the debug flag to the code. There is no optimization flags as well. It's also possible to specify libraries that you want to use when building. So in this case here, I have my executable, and I want to add, or I want some libraries to be used for that executable. I specify here target link library is simple to BLAS and M. That will, on a Unix platform, make sure that these are used when linking your program. So let's see. So now I have a target link library, BLAS and M. I'm not sure if this will work now because hopefully, yeah, we'll see. Make here build. Okay, and let's see here, make. It couldn't find it, but you can see here that what it did is added these flags here, LM, to your build. So it will add those and use them when building. I probably need to add a BLAS library here to make this work, but this is the way it works. Another nice thing with Cmake is that you can do conditional builds. That is, you can control the configuration depending on the different platforms. And there are a lot of different predefined variables for different platforms. For example, you can there is Unix, Linux, Apple, Win32, and you can use very simple if statements here in your code. So if Unix, then this message will only display when building on a Unix platform. So on a Windows platform, this will not be displayed. And you can use this to create very sophisticated build rules. So for example, if Unix add executable, I want to target link this library I want to use on Unix. If it's not Unix, if it's Windows, I will use a different name of my BLAS library. If it's something I don't know, I just print out not to support the configuration. You can also use your own variables, just like in Make. You use the set command here to set a variable, and you can use the variables in principle like in Make, but you use curly brackets instead. So my message $bracket my var name. You can create lists as well using set my list, and then you just list with spaces between the values in the list, and that will be created a list. And you can loop over the list. This can be used for building in steps or doing pre-processing steps in what is required for your own code. You can also set special optimization flags here using special variables. So Cmake _Fortran flags release. So which flags are used when building using the release version? Which flags are used when doing the debug version? You can also explicitly set the Fortran compiler using Cmake Fortran Compiler. Sometimes that can be necessary because Cmake sometimes is too smart for itself and picks the wrong compiler. So sometimes you need to kind of really explicitly say, please use this one and do not think too much. So this is also an example here. So if Fortran compiler name equals gfortran, I can set these flags, for example. If its compiler is something Intel compiler, I can use a different set of flags. So you can really create a single build file that works on any platform, and you can create a lot of different configurations for different platforms to optimize them specifically for that platform. It's also possible to create generation of project files for many of the different development environments that exist. So Cmake supports Visual Studio, Eclipse, NetBeans, Xcode, and many more. And you can actually list the number of available of this here. So if you do Cmake -help, you can see the different generators that are available. So the default is the Unix Makefiles. So that is what we're using now. It will generate Makefiles in your current build directory. But here you can see here that you have Ninja files, what can we make, code blocks, Eclipse, Kate, Sublime, and so on. And on a Windows machine, you will actually have also Windows project files for Visual Studio Code. So Visual Studio, and on a Mac you will also have Xcode. So that's useful. So for example, you can do Cmake_J, and then you specify the name of your the generator that you want to use, and that will generate the files here. So in this case, you can see it generated .project.c project. And I want also to show. So Qt Creator actually uses Cmake. You probably have seen that already as it. When you create a project using Qt Creator, it will use Cmake. So for example here, if I do a file, new file project, and I select non-Qt project, plain Fortran application, choose. I do my Fortran apps, press next. You can see here that it uses Cmake here by default. So a project in a Qt Creator is actually a Cmake file that it maintains automatically for you. You just click next, finish. And you can see here the first thing it does when you open this new project file is actually, if you look down here, it runs Cmake automatically for you. You can see it loads all the compiler definitions, and when that is done, Qt Creator parses the output and creates this part of the code here. So you can see we have the Cmake file here that is automatically generated, and it has the source code files as well. When you want to add a file in this tool, so for example, if I do file, new file or project, and Fortran, I will add a module file here. My module, you can see here it is in my Fortran application directory. And I do finish. You see I have an empty module here. But you see that it's not updated here. And that is because you need to do the Cmake configuration again for the source code tree to be updated. So what you do then is that you mark the My4 app here. You can do two ways. You can do build, you can do run Cmake here. And now you see it added the My module F90 here to the tree. You can also right click on the target here and run Cmake here. And actually building this thing is just, it calls make. And if something changed, it will, yeah. So it also supports, for example, if you, it's also possible to, if I close everything, close all projects editors. So if I do file, open project, file, open. If I do, let's see here, my Fort app here. So if I do open a Cmake list file, it actually opens the project for you automatically. So Qt Creator can open any Cmake file, and you can use Qt Creator to work on the project automatically. So in this case, if they're open here, you can see it will run the Cmake and create the source code files here, so you can edit your code automatically in Qt Creator. So, and many of the existing development environments for Fortran and C++, most of them use Make at the lower level. So even if you have really sophisticated project management in Xcode or Visual Studio, down to the ground when it's built the code, it uses Make. And I know that Microsoft, for example, uses the Make as a tool for building software. So it's in there, hidden away. But the dependency resolution, everything is done by Make at some point, even if you're using graphical tools like Qt Creator or Visual Studio Code. So that was it for today. Next Tuesday, I will go through the project assignment and talk a little about how to think about when you're creating your project assignment. Already now you can think about what you want to do and send some information to me if you want. So that was that. So let's see here.